Hello everyone, and welcome to week 3 guided study group of Math 141. This week we're gonna cover section 6.6, 7.1, and 7.2, which basically focus on inverse strict functions and some techniques of taking integration, including integration by parts and trig integrals. Having said that, I'm gonna get started for the materials this week. As usual, I'm gonna go through the materials quickly, and then we're gonna do the representatives examples that I think that will appear on your quizzes and self-assessment. I think that's really important to know. So 6.6 is basically inverse trig. So this is a table that I kind of like summarized for you guys about different functions. And I include the functions, the domain, the range, derivative, and related integral. This is kind of I think you guys gonna have some time looking at this table later. When I posted this slide. And then the thing that I really think that is very important to remember is the domain. A lot of the time, my students just overlook the domain, but in this inverse trig function, it's really important because it will affect that your final answer if it's correct or not. Most of the time, my students get it to the final answer, but they didn't take care of the domain. So sometimes their answer is they have more than enough answers, or they forget to eliminate one because they didn't account for the domain in their answer. For inverse tangent, and inverse secant, I just want to include that graph here because I think it's really important to kind of like know these graphs so that you get a it's easier to remember things by images than by than by wood. So I just put it. Excuse me. And this one's gonna be pi over 2. This one's negative pi over 2. This is 0. And then that's the graph of sine. The graph of tangent is this. It's gonna approach the horizontal asymptote at negative pi over 2 and pi over 2. It's going to infinity. Hi, Anthony. Can you please identify your PSU ID in the chat room so that I can kind of like keep track of the people here? I kind of like already get started on reviewing, but let's get this. Okay. So what I just did is that I quickly go over this table. So this table is kind of like my summary about the inverse trig function with the function domain, range, derivative, and related integral. For now, I think it's really important to remember the domain, the range, derivative. I would say like all of them are really important for different reasons, but the most important reason is that inverse trig function is not like the regular trig function. So trig function, you have the domain BR, so it can be from negative infinity to infinity. But for these inverse trig function, it can only have its inverse exist when it's a one-to-one function, and these domain and range are the reason that it can be a one-to-one function. So that's why I think it's really important to remember. The derivative and integral is important throughout because now we're going to learn about, after this, we're going to learn 7.1, which is technique of integration. And so this thing is becoming to be important in the next section. And so I just kind of like quickly go over the graph of these because sometimes I think it's much easier to remember the graph or like learn by images than by words. So what I have here is that I have secant is from, so this is 3 pi over 2 pi over 2. So we have this. The graph of secant is slightly hard, so it's up to you if you want to remember it or not. So we have it graph here. Set 1. This is pi over 2. But I think the graph of inverse sine, inverse tangent is the important one. Then we have the right triangle relationship. This is a very, very important relationship because a lot of the problem in this section, next section, and I mean at least for the materials of midterm 1 is going to use a lot of right triangle formula, because what we're going to do later is that we're going to have one technique of finding integral where we put x as inverse tangent of an alpha angle. And after that, your integral is going to become all in alpha. So alpha now is going to be the variable instead of x. So after you solve that integral, the right triangle technique is the one that will help you to put the integral in the final answer in alpha back into x, because that's what we're looking for. So the right triangle relationship is really important. And how it works is that, say if you have, most of the time this is what we're going to do. So say if you assume that x is inverse tangent of alpha. So this is alpha inverse tangent, meaning you have tangent alpha to be x. Oh, if you assume that x is tangent alpha, so then you have x over 1 beta. Sorry, I think I say it wrong in the previous part as well. So, but just the one that when I start talking about right triangle relationship. So when you assume x as tangent alpha, this is what you have. And then your hypotenuse is going to be x square root of x squared plus 1. So this is the right triangle. So if you have, say, your integral of something be alpha, then what you want to do is that you want to put, or maybe it becoming, say, like, yeah, alpha. So you can put the final answer in back in the form of inverse tangent of x, or you can put it as inverse secant, inverse sine of x over x squared plus 1, take the square root. So there's several ways that you can put the final answer in. But this is the way, the biggest application is that to put integral in alpha into the function of x again. So that's what we have. Now we're gonna do the examples, and you're gonna see what I mean. I think not this week, but later. Maybe actually it was this week, or maybe the first two sessions of next week. But anyway, the example 1 is asking us to find tangent of inverse cosine of 3x. This is also one of the way that you're gonna use right triangle formula. So we have, this is an angle inside of tangent. So if we say alpha is this angle, so you have alpha is inverse cosine of 3x, meaning you have cosine of alpha is 3x. So this is going to be 3x divided by 1. All I can rewrite is this way. So it's adjacent divided by hypotenuse. So the final sign, the opposite sign of the angle is going to be 1 minus 9x squared, and you take the square root of that. So your answer for tangent of alpha. So I replace the inverse cosine 3x with alpha. Then my tangent of alpha is going to be square root of 1 minus 9x squared over 3x. So that's my answer for this question. So for these kind of questions asking you to find trig function of an inverse trig function, then you use the right triangle formula. So trig function of an inverse trig of something, then you use right triangle formula, or you can use the right triangle relationship, doesn't really matter. So doing the same thing, we're going to do that for secant of inverse tangent. So this is alpha. So you have alpha is inverse tangent of 12 over 5. So meaning tangent of alpha is 12 over 5. So you're going to have 12 over 5. If you use the Pythagorean theorem, then you principles, then you can find the hypotenuse be 13, which is square root of 12 square plus 5 square. Then you have secant of alpha is 1 over cosine alpha. So cosine is adjacent divided by hypotenuse. So secant is going to be hypotenuse divided by alpha divided by adjacent. So that's my answer. So again, the lesson from here is that for these kind of questions where you ask the trig function of an inverse trig function of something, use the right triangle formula. Now we go to example 2. Example 2 is talking about asking us to find the limit at x approaching negative infinity of inverse cosine. And this one has a lot to do with the range, the domain, and especially the graph. If you remember the graph, this thing should be really easy. And so what we're going to do is that we have limit x approaching negative infinity inverse cosine of a minus x square root of 3 divided by 4x squared plus 17. This one is going to equal inverse cosine of this limit. We'll take this limit inside. 8 minus x square root of 3 divided by 4x squared plus 17. Now all we need to do is that we're trying to cancel out that x because we're trying to arriving at the final answer, which is a number for a limit to exist. So what we're going to do is that in the numerator and denominator, I try to take x out, so we have x here. All we have left is a over x minus square root of 3 divided by. Now if you want to take x out of here, what you have to do is that you want to take x squared out. So outside is going to become absolute value of x with square root of 4 plus 12, 17 over x squared. Now this absolute value of x makes the entire thing become negative x square root of 4 plus 17 over x squared. Why is that the case? Because when you take x squared out of the square root, it becomes absolute value of x. But x is approaching negative infinity, so it's a negative number. So for absolute value of x, there are two cases. It's going to equal to itself if itself is bigger than or equal to 0, or become the opposite of itself if it's negative. So x is approaching negative infinity, so it's a negative number. So after you take it out, it's going to be a negative x. So negative x 4 plus 17 over x squared. So now you can easily cancel out that x. And so our inverse cosine now become limit of x approaching negative infinity 8 minus a over x minus square root of 3 divided by negative of 4 plus 17 over x squared. Now a over negative infinity is going to be 0 minus, which is a very small and negative number, but you can ignore it because it's very, very small compared to negative square root of 3. So it's going to be inverse cosine of negative square root of 3 divided by negative 2, which is going to be inverse square root of 3 over 2. Now this is where you come the range of the answer, because now coming back to this, for inverse cosine, your range can only be in from 0 to pi. So whatever your answer for that angle is. So the range is that when you have inverse cosine of, say, a number is half, your answer can only be one angle. It cannot be two angles as we usually did. Okay, if you have cosine of 1 equal 1 over 2, how many angles can we have? That one is not the same as this one because now you inverse cosine. So your range of your answer can only be from 0 to pi, and it cannot account for the one below it. So in this case, your answer is going to be this answer have to belong from 0 to pi, which is going to give us inverse cosine is square root of 3 over 2. That one is going to be pi over 6. So that's my final answer for these questions. Usually for these questions, you can also have the answer be negative pi over 6, but that one is not in our range, which is from 0 to pi, so you cannot account for that negative pi over 6. So that's example 2. Now example 3 is finding the derivative of fx, which is equal to inverse tangent of x to the 2 to the x. Now this one is where I want you guys to use the logarithm differentiation in combination with the derivative of inverse trig function. Now this one is gonna make the problem really long and really complicated, but as long it really tests how much you guys understand the material, because there are only two things that we need to know in this question essentially. That is how to take log differentiation and the derivative of inverse tangent. So that's what we're gonna do. So as usual, we call this one y equal to inverse tangent to the 2 to the x. And now, when we take the first step in taking log differentiation is taking ln of y equal to 2 to the x times ln of inverse tangent x. After that, you take derivative of both sides. You have y prime over y is 2 to the x ln of 2. So this one is what we learned last week about the exponential and log function and what is their derivative and integral. So you have that multiply. Now with that, I'm using product rule right now. So now ln of inverse tangent, and you want to take derivative of that, is going to give you inverse tangent of x in the bottom, and you have 1 plus 1 over 1 plus x squared here is actually just the derivative of inverse tangent, which we have to take by chain rule. And so your final answer of y prime become y times this entire thing, which is just going to be inverse tangent of x to the 2 to the x multiply 2 to the x. The inside we have ln of 2 multiply ln of inverse tangent x plus 1 over 1 plus x squared times inverse tangent x. So that is my final answer for this questions. So again, as I said, there are only two things you need to know, but it's up to you if you have like the kind of the solid understanding that you can go to the end of the problem. So before I get to the next sections, is there any questions for this problem? Okay, I'm gonna go to the next section. So which is 7.1. So 7.1 is kind of like where we talk about technique of integration, where we're gonna learn about integration by part. So this is kind of like, before we go to integration by part, this is the kind of like the general summary of all of the formula that we have so far. I took this one from your slides because I think it's a very important one and it's really easy to review. Assume that there's ones that you're gonna forget, like the formula of this part because it's like not a basic integral. It's kind of like an upgraded one already. So this is a very good table to refer to. Then we have the technique of integration by part. So the technique of integration by part basically asking you to put your integral into the form of an integral of UGV, with U and V are two different functions. It may be trig with exponential, log with inverse trig, something like that. The integration by part is especially used for integral of two different functions. Most of the time, it is really easy to see that there are two different functions existing um, in your given problem, but sometimes it can be very subtly shown as well. But I think it's gonna come a lot from your practice. So do a lot of practice, and if there's something, say usually if you see an integral that is super short, that you only see one function, but you don't know how to find out because it's not a basic integral, then most likely you have to use integration by part. So you put that into the product of UdV, and then that integral is going to equal u multiply v minus the integral of v du. And usually this v du will be much easier to find because the order that we're going to choose, what is u and what is v, is given here, and you can remember its abbreviation called ILATE, which is going from inverse trig to exponential. And then there are some important integrals. I put it in the previous slide, but I also included it here because they're kind of new and you guys haven't seen it in 141 much at all. I think this is going to be the first time that you guys see these here. But it's really important sometime that you guys remember this. I'll show that in one of my examples. If you remember one of these, it's going to be just within seconds that you can solve the problem. So example 4 is first finding the integral of e to the x cosine of x dx. And so this is for first thing, as I said, integration by part is for integral of two different functions. And so we have exponential here and trig here. So if we look at the order to choose u, we're going to choose u be the trig function here. So let me call this one I. It's easier to control. So now we're going to put u as cosine x du equal negative sine x dx. dv is e to the x dx, and vb e to the x. Then your I now will become, so this is u, and this 2 be dv. So it's going to be equal u multiply v. So u and v, e to the x cosine x minus and minus is a plus. So plus e to the x sine x dx. Again, now we have another one to take integration by part here. So you put u as sine x. Trust me, this approach might seem that it's not going anywhere because it seems to repeat itself, but finally you're gonna get the answer, and that's the magic to this kind of problem. du is cosine x dx. dv is again e to the x dx. v is gonna be e to the x. So now your I is going to equal e to the x cosine x, that was rewrite it, plus e to the x sine x minus e to the x cosine x dx. Now from here, at this point, you don't do integration by part anymore because now it comes back to your initial integral. This is just I. So we're just going to take this I over here. So you have 2I equal to e to the x cosine x plus sine x. Or you have I become half of e to the x cosine x plus sine x. Or you can add a plus c if you want, because it's an indefinite integral. So it cannot be just a number, it's a function. So the magic to this question is coming from here, that you come down to this point, and you can notice the fact that it's I. Of course, you have to go through this step first, and don't lose the motivation thinking that is I'm just going around and around and it's not going anywhere. That's example 4. Example 5 is kind of like the same thing, so I'm gonna quickly go over it because it's just basically the same step. If you follow that order of taking integration by part, what is u and what is v, then it's gonna be really quick and easy. So here I have, so it's go I late. So log first and then polynomial or just algebra, which is 8. So calling this one I, we have u equal to ln of 2x, and you have du be 1 over x dx, dv be dx over x squared. Now this is a very important one to remember because this is just, you can rewrite it as going to be x to the negative 2 dx, which if you use you have v is going to be negative 1 over x. All you have is going to be negative x to the negative 1. So this is just the integral of a polynomial. So then we have I equal negative 1 over x ln of 2x plus 1 over x squared, take the integral over dx. So now again you're going to have negative x 1 over x ln of 2x plus 1 and go from 1 to 2. So your I now is going to become negative 1 over 2 ln of 4 plus negative 1 over 2 plus because it's a negative and that negative, so 1 multiply ln of 2 plus 1. So your answer now is going to be, so ln of 4 is basically negative 1/2. ln of 4 is basically negative 1/2 multiply 2 ln of 2. So I rewrite 4 as 2 squared and take that 2 outside. So you have that is going to equal ln of 2 1. So this and this cancel out. So what we have left is just half. So that's my final answer. So again, this is the thing I want to introduce you is this step. Most of my students already forget it at the time that they come to this point. So it's just a quick reminder that there are several things that can go along with one problem of integration by part. So the technique might seem very easy and if you follow that order, but there are many other things that are coming along with it. And usually they don't just test one thing, actually, because the exam is, it doesn't say that it's cumulative, but most of the time the materials build up on one another. So it's kind of like cumulative in concept. Example 6. Again, I'm gonna do this one quick, but before that, let's think about it first. So you have a polynomial with a trig. So by definition, you're gonna take u as x by the order, and then dv as tangent square dx. But just think about it and looking at this table. Looking at this table here, there is no integral that will give you tangent square on this side. So we have to do some manipulation here first. So one thing we know is that tangent square x plus 1 is 1 over cosine x square equal to secant square x. So some of you will be like, how do I know this? Like, there's so many things to remember. That is true, but you guys already learned this one. So when you learn about tangent x and you take derivative of that, what is that become? What is that becoming? It's tangent square plus 1 or secant square x. So just by this part, it's like subtly given, but now you have to use it. So I'm going to rewrite tangent square as 0 to pi over 3 x, tangent square as secant square x minus 1 dx. So my problem now is going to become two different into two separate integral x dx. So again, I'll call this one I, and then I'll resolve the first part first. So I put u equal to x, du is going to equal to dx. Then you have dv is secant square x dx. And as I said here, your v now is going to be tangent of x. So your I become x tangent of x minus x minus tangent x dx from 0 to pi over 3. And then we have that part here, so which is going to be x squared over 2 of 0 to pi over 3. Now, it's going to be really easy if you remember the integral of tangent, which is ln of absolute value of secant. So it's gonna just, that's what I'm saying. If you remember that, it's just gonna take you a second to do the problem. Especially in this case, your exam is going to be multiple choice. So you don't even need to go through all the pains of proving this thing from that again. So it's gonna be so much easier. So that one I'm going to take from 0 to pi over 3. So we have pi over 3 into pi square root of 3 minus pi square over 18 minus ln of 2, because secant of pi over 3 is 2 because it's 1 over cosine, and cosine of pi over 3 is 1/2. So that, and then the rest is just going to be 0. So your answer is, this is your final answer. So the important here is sometime before you jump into doing integration by part, because you can notice immediately that you have two functions existing in your problem. You have to do some manipulation first, and there are a lot of other relation that you need to know. But for now, that's all I put it there. But I think if you go through the problems that your Dr. Kasher suggested, then you will gradually collect all of them, and you can put them in the list that you can refer to later. And you won't be too surprised when you come to the quiz and the weekly self-assessment. So that's all I have for 7.1. I'll go to 7.2. I think this section which is trig integral. So this is I think this is like the easiest among all of the problems so far. So it's usually going to be in two form. The integral of sine to the m times cosine to the n dx, or the integral of tan to the m and secant to the n. So I put below that is that all the thing that I put is all of the things that you need to know to do this kind of problems. And they're just going to be around u substitution, using half angle identity or double angle formula identities, and then this very important is cosine squared plus sine squared equal to 1. And that's all we need to solve this kind of problem. Then we have for tangent and secant, again we use u substitution. This are relations that we just used in example 6. And then some extra thing is these integral that I already mentioned at the beginning of this section today. Now, having said that, all we need to know, now we're just going to jump into the example. And I think it's going to be really easy as long when you see me did it for the first time. So for sine and cosine, it's going to be only between u substitution, half angle, double angle, and sine squared plus cosine squared equal to 1. Here we don't see any double angle or half angle, so we don't need to care about those two. So the rest is just going to be u substitution and sine squared plus cosine squared equal to 1. So you have sine fifth, and you can do it both way. You can put u equal to after this, so I can put 1 over sine squared x cosine x dx. So this cosine cube I rewrite as cosine square x times cosine x, or you can rewrite as sine square x times sines 1 minus cosine sine square x times cosine x. Or you can also do that for sine, where you rewrite as, so you have sine fifth. So you can rewrite it as 1 sine fifth x can be 1 minus cosine square x square multiply sine x, and then you put u equal to cosine x. Du is going to be negative sine x, but that I don't want to take care of the square, so I didn't use that approach. But at home, when you retry this problem, you can do it this way to see if you are very you have already mastered these sections. Now, having said that, I'm just going to put u equal to sine x here. Then I have du be cosine x dx. Then of course, because this is a definite integral, always you have to do the change of variable. So you have x going from 0 to pi over 2. So u is going to from 0 to 1. So now your integral is going to become from 0 to 1 u fifth 1 minus u squared multiply du. See, doing it this way already helped you to simplify the problems a lot. And now all you need to do is just gonna distribute them in and take the very easy integral. So 1/6 minus 1/8, which is going to be 1/24. So the technique here is just rewrite sine fifth and cosine third in two different ways, and then you use substitution to do the change of variable, put everything into the form of u. And then you're just gonna solve it. Similarly for the tangent and secant, what I'm gonna do is that I'm gonna rewrite as pi over 4. So now for this one, I think in your lecture notes, Dr. Kasher, remember it in several ways. Say like if you have the 2 power are 2 power even, 1 odd, 1 even, and all of that. But I think it's really confused. Sometimes be really confusing to remember, because the material for exam 1 is not just going to be this section. And so I think if you do enough practice and you know all of the materials you need for just that section, say as all I did, then as you do the problems yourself, you have that instinct of seeing that problem out instead of remember words by words. Like say if you have M is odd, N is even, or something like that. So, but that's just my opinion. So here you have, I'll rewrite secant fourth as secant square x multiply secant square or tangent square x plus 1 multiply tangent cube x dx. Why do I do that? Well, because immediately from here, if you have u equal tangent x, du is going to be secant square x dx. So if I rewrite this way, I can eliminate the secant square when I do the u substitution. So if I put u equal tangent x, du is going to equal secant square x dx. Again, do the change of variable. 0 to pi over 4. So it's going to be 0 to 1. So your integral is going to be from 0 to 1. This secant square with dx is du. U squared plus 1 multiply u cubed, which is going to become u6 over 6 plus u fourth over 4 0 to 1, which is 1/6 plus 1/4, giving me 5/12. So again, this is my final answer for this questions. Again, all of the materials and all of the techniques that you need to use for the sections, I already put in the slides, and you can refer to that after I posted it. If you don't have any further questions, then I have some practice problems, and I would highly recommend trying them out because they're a little bit more challenging than the problems in the book. But I would suggest before that you should try all the suggested problems that your instructor have in Canvas. If you don't have any more questions, I'll end the sessions here and I'll see you guys next week. Thank you for coming today.